We're going to find a thing called derivatives, and we're going to look at them as rates of change. At least that's what the chapter heading is called. Essentially, we've got two very short introduction things to do. First thing is we're going to look at how do you find the slope of a tangent line using limits. So all that work about using limits was to get to here. And we're going to return to the tangent line problem, and we're going to show you that we can find the exact value for the slope of a tangent line. And the derivative is just another name for the exact value of the slope of a tangent line. It's easier to say one word than to say every single time the exact value of the slope of this tangent line, right? So we call it a derivative. So it's probably anticlimactic, but that's what a derivative is. And we are going to look at how we can use limits to find it. And then we're going to use a little application of it, which is we're going to use derivatives to find velocities and accelerations of a position function. So first thing is some skill building. We need to just revise a little bit about functions. So imagine I have a function, and I'm going to make my life pretty easy. I'm not picking anything particularly ugly. And we have this, we call that function notation. You would read that out loud as what f of x is x squared plus 3x plus 1, right? That's a function. Now, if I write down f of 5, we should all say, oh yeah, they mean x is 5. And f of 5 is the value of this function when x is 5. So that's what, 25, another 15, that's 41. And we get f of 5 then is 41. And I hope, at least if you got me, I know that you would get this, that you can also replace the x, not with a number, but you could replace it with, say, a. And if I asked you to find f of a, you would start with the original, put a little bubble around it to make it more obvious that that's the starting point. You start with the original, and the x's gets replaced by a's. So you would have a squared plus 3a plus 1. And you can even find things like the value of the function at a plus h. And that's a little bit messier, but it would be a plus h squared plus 3 lots of a plus h plus 1, right? And it would be worth to make this a little prettier. Now, a plus h times itself is not, let me phrase this again, it is not a squared plus h squared. That mistake drives me crazy. If you do a plus h times another a plus h, you should be foiling it. A plus h times a plus h. And so what you really do get, and you can check this out on your own time, that's what a plus h squared looks like, right? You notice there's a middle term. That's very common for people to miss that. Then 3 lots of a, 3 lots of h plus 1. And if it was possible, I'm shouldn't you collect like terms and make it look prettier. But from what I can see, aren't all of those terms slightly different from all the other ones? So that's pretty much as good as that's going to get. So that was just a little skill building exercise to remind us how to work with functions and how you can evaluate them at numbers. You can evaluate them at a single variable, say a or b or h, whatever you feel like. And you can even evaluate it at things like a plus h. Ring some bells. Can you remember doing things like that way back in 141? Right. Nothing too shocking. Good. So now we've got that guy out the way. Let's look at the tangent line problem one last time. So imagine you have a curve y equals f of x, and I would like to find the slope of the tangent line. There we go. We'll call it M, right? I want to find the slope of that line. Well, what we would typically do is we'd find another point on it. Let's call this point Q. And we'd find the slope of the tangent, not the tangent line, the secant line, PQ. Remember that guy? And that would be an estimate because, in fact, if you look at my example here, it's a pretty bad estimate. Would you agree that the blue pen is quite a far distance away from the real slope, which is meant to be the red pen? But we know it's an estimate and we will start from that perspective. So it's going to be the rise over the run. And if we can make Q really close to P, right? So if we pick a point on the curve where Q is like here, won't the slope from P to Q be really close to being the same thing as the slope of the tangent line? So now we're going to generalize that. What do I mean by that? I do not know what the point P is, right? So let me tell you that it's going to have an x coordinate of A. So A will have coordinates A, comma, f of A. You comfortable with that? Now, what about Q? I don't know, I should stick to red, I guess. The x coordinate of Q is some point just a little bit bigger than P. And I'm not going to call it B. I'm actually going to call it something a little bit less obvious. I'm going to call the x coordinate of Q A plus H. Now, as long as H is a very small number, won't A plus H be quite close to A? Now, what's the y coordinate of Q going to be? Well, since it's on the curve, it's going to be f of A plus H. So far, so good. Now, the slope of the secant line, the rise over the run, can be given as the y coordinate of Q, take away the y coordinate of P, over the x coordinate of Q, take away x coordinate of P. So that guy there, for instance, is the x coordinate of P. This guy here, the y coordinate of P. X coordinate of Q, y coordinate of Q. So the slope joining P to Q, if this is the coordinates of P and this will be the coordinates of Q, then the slope of this guy becomes that guy, f of A plus H, take away that guy, f of A, over A plus H, take away A. So it ends up being this thing. So if I want to find an estimate for the slope of the tangent line when x coordinate is A, this would do it, right? If you make h 0.1 or h 0.0 or point anything, this would do it. And here's where the limits come in. If you find the limit as h tends to 0 of the slope of this secant line joining P to Q, which is given by this expression, what you're physically doing here is, aren't you bringing Q infinitely close to P? In other words, you're shrinking it down to it isn't even there anymore. Now, normally that would cause a problem because if you tried to do it as a number, which we did in week 1, don't you get 0 over 0? But we can avoid that 0 over 0 problem by making this a limit process. So we're not making it 0, we're making it as the limit as h approaches 0. which sounds like it's a lawyer, but it makes a difference. This guy here is the slope of the tangent line. And we call it the derivative. And its full title is the derivative of f of x at, it says at x equals a. So the slope of a tangent line is also the derivative of the function at x equals a. But that's a mouthful. So we use this notation. F dashed of a. So our first derivative is going to be found using this formula. It's a fundamental formula in calculus that allows us to get the slope of tangent lines. F dashed of a is the limit as a tends to 0 of this fraction. Well, let's put it into practice. I would like to know, where's that guy gone? I would like to know the exact value of the slope of the tangent line of this quadratic at x equals 2, right? So that's my question. Let's find that. So we're going to find the exact value, because that's what this will give us, an exact value of the slope of the tangent line to the function f of x equals x squared plus 3x plus 1 at, I think, did I say it 2? Doesn't matter, just want to be consistent. Okay. Right?
Yeah, you said 2.
Right. So at a equals 2, right? Or x coordinate is 2. Now, we could write that whole thing, or we could just say to you, find f dashed of 2. I mean, would you agree that's much easier to say than having to say this sentence every time? And you read that out as f dashed 2. Unless you're American, in which case you call it f prime 2. But I refuse to call it f prime 2. I'm too old to change my ways. It's f dash 2. Right? But you can call it f prime 2 so that when you go to university, your professor won't laugh at you when you say f dash 2 and they think, what? Yeah. Right. So let's do that question. I want to find f dashed of 2, right? The slope of the tangent line at 2. So it's going to be the limit as h tends to 0 of 2 plus h. I take away the value of the function at 2 over h. Have you noticed that the a is now the number 2? Right, because that's the guy we're going to use. Now, this is a lot longer than you will normally do this, but I want to just take this as slow as I can. There's the original function. The value of f of 2 then is 2 squared plus 3 lots of 2 plus 1. So that's 4 and 6 and 1, that's 11. F of 2 plus h, well, that's going to be 2 plus h squared plus 3 lots of 2 plus h plus 1. If you FOIL that out, you get a 4. You end up with a 4h and then h squared. If you multiply this out, you get a 6 plus a 3h and what, plus 1. This time we can do a little bit more collecting of terms. So there's an h squared. that guy and that guy gets me what, 7h. This guy, and this guy get me 11. Okay, so I've got all the pieces that I need to calculate this limit. So f dashed of 2 is going to be the limit as h tends to 0 of f of 2 plus h, which is this, take away f of 2, which is this, all divided by h. So if we find the limit of this ugly fraction as h tends to 0, won't I be finding the slope of the tangent line at 2? Well, let's see what we get then. Well, they cancel out. And I get that. And I'm going to use factor and cancel. I'm going to pull out h as a common factor. Right, so I'm using factor and cancel method. Common factor of h. Now I'm going to cancel. 1 for 1. So we get the limit as h tends to 0 of that guy, which is dead easy because 0 plus 7 is 7. So the slope of the tangent line of this quadratic when the x coordinate is 2 is exactly 7. That is not an estimate. That is the exact value for the slope of the tangent line. We have now solved the tangent line problem. We can find the exact value of any function that you like within reason by using limits. That's pretty cool. Any questions so far?
You were solving you gave the example f2 plus h minus f2 over h.
Yes.
Where did the x squared plus 3x plus 1 come in?
That came in because this was the function that we were going to find the slope of the tangent line at 2 from.
Oh, okay.
So this here will change every time, right?
Okay. Yeah. Can I take a picture of that whole page here?
There we go.
All right. Thank you.
Well, as much as can fit. These videos do appear back online later this evening, so you can always go back and have another look at things if we didn't get it. Now,
So, hey, Professor.
Yes.
So I actually tried taking this course before, but had to drop it. And I did get through that part, and that was one of the things that was hardest to wrap my head around was where does that come in? But I think what helps me now is remembering that those are functions, and the function is that equation. So laying it out first and then just filling in the blanks with the a plus h and the a, just like we would any other function, is a helpful reminder, because I used to get lost doing this.
So you don't feel if I'm picking you up right and putting words in your mouth, the second time around it was easier to get your head around.
Yeah.
Right. Okay. Good. I like that. So let's pick a function. We'll keep them simple because this process is quite long. Can you imagine how much work there would be if it was a huge, massive function this size, right? You'd be here all day just doing one question. So we tend to keep these functions relatively simple for that reason. And then later on, I'm going to tell you, hey guys, there's an even quicker way to do it. But for now, I'm not even going there. So let's pick a function. I'm going to pick a x cubed, right? Actually, in the big scheme of things, x cubed is pretty boring, isn't it? It kind of looks like that. Good. How And we'll find the slope of the tangent line at any point you like, right? At the x coordinate of 2 or 3 or 50 or whatever. I don't want to pick 50 because you can imagine how big the numbers are. So let's do it at, let's say, x equals 1, which basically means a is 1 then, right? Whatever the x coordinate is. So it'd be roughly about, I don't know what my scale is, say there, right? So if I'm doing this correctly, shouldn't the slope of this tangent line at least be a positive number? Now, how steep it is depends on the scaling that I use. So don't pay too much attention if the answer looks bigger than 1, because it probably will be. In fact, I believe the answer is going to be 3. So let's find the slope of the tangent line at x equals 1. And I better have my, where's my standard formula guy? Here it is. This is our go-to guy, right? This will get our thing done. So I'm going to be looking at the limit as h tends to 0 of 1 plus h, because a is 1 in this question. Take away f of 1 all over h. Now this time I'm not going to do every single line that I did the last time. So you will fill in the extra working yourself later. This fella, focus, isn't it? This fella here is 1 plus h cubed. Agreed? The function is x cubed. F of 1 plus h is 1 plus h cubed. Takeaway. Isn't f of 1 just 1? Because 1 cubed is 1. So I'll just do that. And the whole thing is over h. And so we now have the limit as h tends to 0. That fella. I know that guy is not 1 plus h cubed either. That one involves you going 1 plus h times 1 plus h times 1 more 1 plus h. And I'm just going to tell you the answer. And you're going to be amazed at how quickly I can do that. But there's a cheat called Pascal's triangle. So if you want to go and look that up, Pascal's triangle, it'll show you how you can do that. Otherwise, you just FOIL it the way you would. Now, there's not an awful lot of collecting like terms there, would you agree? Or cancelling, but don't the ones kill each other off? So in this case, I have a 3h, I have a 3h squared, and I have an h cubed over h. Let me pause now. Whenever you use this formula, there is going to be a line that looks like this. All the stuff that's left on the top will have an h in it. Right? It might be h squared, it might be h cubed, it might be 5h, but it will have an h in it. If you have a +7 or a -2, right, a number on its own, you have done it wrong. Stop and figure out what went missing. Because the way the math works, this process always generates, eventually, nothing but h's and h squares and square root of h's, whatever, right? Things with h's in it. Always does it. No exceptions. And because of that, can't you pull out a single h as a common factor? So we're doing factor and cancel again. Now, if you cancel this one with that one, you now are going to be getting the limit as h tends to 0 of 3 plus 3h plus h squared. Right? And h is 0. Can't you just say 3 nothings and nothing squared? And so there's the answer that I told you it was going to be. The slope of the tangent line to x cubed at x equals 1 is exactly 3. Pretty cool. We have a process that allows us, using limits, using this formula, to find the exact value of any function, theoretically at least. So this time I'm going to make life difficult by choosing a pretty innocuous function, the square root of x. Square root of x, right? Non-special, it looks a bit like that. And I would like to know the slope of the tangent line at 4, right? So if you imagine here is 4, my tangent line would be something like that, right? I want to find the slope of the tangent line at x equals 4. So that's going to be the limit as h tends to 0 of the function at 4 plus h, take away the value of the function at 4 all over h. Now the algebra is a little bit uglier this time. F of x is the square root of x. F of 4 plus h is the square root of 4 plus h. F of 4 is just the square root of 4, so that's 2 all over h. Are you comfortable with our replacements, right? So it's the square root of 4 plus h, take away the number 2 over h. And we are trying to find the limit of this fraction as h tends to 0. And this is why some of the things that we did earlier on, this is why we did them. Don't we need to find a way of dealing with this question? Can you see what method we're going to use to solve that ugly fraction? What's it called? Even has its own name.
Conjugate.
Called a conjugate. Whenever you see a square root, don't you think conjugate? Right? That's what my brain says. Square roots, conjugates, right? End of story. This might be a little bit small, so I'll tell you it says the square root of 4 plus h add 2. That's what that is saying. You can't see it. And I'll move it a little bit over here for room. So the slope of the tangent line at 4 is now going to be the limit as h tends to 0. The two guys in the bottom, don't do anything to them. Just write them down as two things multiplied. Now, if you take this guy and you multiply it by that guy, right? This fella times that guy. I'm going to do this one over at the side here. So I'm going to take that, the original, and multiply it by its conjugate. Now, the shortcut is that when you do this, you always get this guy squared, take away that guy squared. But let's show you kind of the long way. FOIL. The square root of 4 plus h times itself gets you 4 plus h. That's f done. The outside, that's these two, the O. This square root times plus 2 gets you 2, the square root. And that's the O. The I, well, negative 2 times this square root gets you negative 2 times this square root. And that's your I. And L, well, negative 2 times positive 2 gets you negative 4. And here is your L. Now, those two guys will always kill each other off, because essentially this is the difference of two squares. And so what I've got is a 4 plus h take away a 4, and the 4s cancel out, and all I'm left with is a rather amazing and very simple looking h. So this times this is just h. And something really pretty happened. This cancels. Remember to leave a 1 behind. So we now have the limit as h tends to 0 of 1 over the square root of 4 plus h, add 2. And when we get to this stage, you can just replace the h with 0 and there is no damage. You get the square root of 4 plus 0, add 2. Square root of 4 is 2, so 2 add 2 gets you 4. And there you are. The slope of the tangent line to the square root of x at x equals 4, it will have a slope of a quarter. I remember, not specifics, but I remember the first time I did this, and it was like one of those, wow, this is cool. I can now find slopes of tangent lines exactly. And then when you see where this leads to, right now, this doesn't look like it's going anywhere. Well, it's a nice little oddity. You can find slopes of tangent lines, no biggie. That's just the beginning of this. Once you know how to find derivatives, right, slopes of tangent lines, it then just explodes out into the sciences. Because a lot of the things that scientists do are they work with rates of change. And rates of change are really just derivatives. And so pretty much anything you can think of in science will eventually end up using derivatives somewhere. Without calculus, we'd still be working with a very limited ability to understand the universe. Right? You can't be a physicist without calculus. Right? You couldn't do the stuff you did. Right? You couldn't even send somebody to the moon without calculus. I'm sure of it. Right? The math in there, it's like the blood that keeps everything alive. Right? It's what gets used. Very biggie. Even this right now, it doesn't make you think, wow, to me that was, oh, I can see where this could lead to. This is good stuff. So that's our second one. Let's make life even more difficult. We'll make a 4. I want to find the slope of a tangent line to a fraction. So we've done quadratics, you know, x cubes and things. That's polynomials, really. We've done square root. We just finished doing them, so that's how we deal with that. Now let's look at very simple fractions, 4 over x squared. And I would like to know the slope of the tangent line at a equals 4. Just because I want to. So this exact value at 4, it's going to be the limit as h tends to 0 of this guy. Take away this guy all over that one. And this fella now becomes 4 over 4 plus h squared. Ugly. Take away, well, if you evaluate this at 4, it's 4 over 16. So it's basically take away a quarter all over h. And this is doable. Can you look at that and you're going to hopefully say to yourself, oh God, this is going to be ugly. Right? This is not going to end well, right? Does that seem reasonable? Right. And I'm sure the first mathematician who came across this problem said, that formula that we've been using, it worked really well when it was a polynomial, right? 5x squared and 3x cubes. It worked really well. It worked really well when it was square roots. But the math that you get when it's a fraction is just scarily ugly. Now, could I do that? Yes, I could. I could fight my way through that and eventually get the answer, but I don't want to. So what they did is they said, can we come up with a different formula for finding this guy that might work better for situations like this fella? So if you don't like the math, right, if you don't like it, change it. Right? What we're interested in is the exact value for the slope of the tangent line. We don't really care what version we did. So you might think, how could they come up with another version? So let me show you the second and last version, right? There are no more versions after this one. I'll have to do this again. That's better. Right, so you have your curve. I'm not sure what color my curve is, green. Right. My y equals f of x again. I had my point here, we'll call it P, right? And I have my other point here called Q. And I have this guy here at A, and P has coordinates A, comma, f of A, right? Isn't that really the same start as we did last time? Now, what we did last time is, didn't we call this guy A plus H? Well, let's call it X, which means that Q has an X coordinate of X and a Y coordinate of f of X. You okay with that? Couldn't I call that B and this would be B f of B? Could have called it C and this would be C f of C, right? Now, if we join those two together, we can now find the slope joining P to Q. It's going to be YQ, take away YP, over XQ, take away XP. What does that look like? Well, this is going to be XP. This guy here is YP. It's going to be XQ. This is going to be YQ. So we have f of X, take away f of A, all over X minus A. You see the formula looks a little bit different now, doesn't it? Doesn't have A plus H's in it, and H's. It has X's, X minus A's in it. And so won't the slope of the tangent line be the limit as X tends to A of this fella? Now, what does X tends to A look like? Aren't we saying this X becomes A, right? Aren't we making P and Q come together? Right? So it's the same kind of idea, but a different approach. This fella is called a derivative as well, or a derivative formula. Now, I could have went back to the questions that we did today and used that formula, and we would get the exact same numerical answers that we got to all the other questions, right? Including the square root ones, right? So you trust me that this works as well, right? So let's have a shot at that fraction question that we were doing a minute ago. So we had a function that was 4 over x squared, and we were going to evaluate it at Well, x equals 4, wasn't it? So the slope of the tangent line at 4 is now going to be the limit as x tends to a, so x tends to 4, of f of x, take away f of 4, over x minus 4. Have you noticed that all the a's are now 4s, right? Everything that says a here is now a 4. Now that becomes the limit as x tends to 4 of 4 over x squared. Plug 4 into there and you get take away a quarter all over x minus 4. Now, have I got that ugly guy that we had a minute ago? Now you look at them side by side, you might not think that there's much difference, but actually this is going to be easier to solve than that. The big problem is, isn't that 4 plus 8 squared just going to grow into an ugly monster, right? At least these are right, tidier bits, right, smaller bits. So I am not going to use a conjugate, but what I am going to do is I'm going to multiply the top and bottom by a special version of 1. And this special version of 1 has got one job. It's to make those fractions go away. Right. Now, if I multiply the top and bottom by x squared, won't that fraction go away? Won't it become 4? If I multiply the top and bottom by the number 4, won't that fraction go away? Right? It'll become a 1. But since I want to get rid of both of them, I will multiply the top and bottom by 4x squared. Essentially, aren't I multiplying by a special version of 1? Right? We don't like fractions, they're very difficult to deal with, so let's get rid of them. That's kind of the thought. So it's now going to be the limit as x tends to 4. This guy times this guy, that guy times that guy, boom, 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 cancel 4. 4 4s get me 16. Take away this guy times this guy, you get x squared. So that's looking pretty. And on the bottom, don't do anything, maybe except put them in slightly different order. So far, so good. So I started with an ugly fraction with fractions in it. By multiplying the top, the numerator, and the bottom by 4x squared, I now have an expression with no fractions, and I got some stuff in the bottom. This question is a factor and cancel. What does 16 take away x squared look like when it's factored? Because it's a difference of 2 squares. Hopefully you can recognize that.
We're going to have 4 plus x and 4 minus x.
Now, factor and cancel. We've done the factoring bit. Somebody here cancels out with somebody here, right? There's a guy in the top, cancels with somebody in the bottom. And we have done this before, so I know that you've seen this situation happen in the earlier questions. What on that top line can cancel out with what on that bottom line?
4 minus x and x minus 4, and then it leaves a negative 1 at the top.
There you go, which I'll just put as a negative, right? Agreed? Now let's see what we have next then. It's going to be the limit as x tends to 4 of a negative answer. And it was what? 4 plus x, that's all that's left on the top. And a 4x squared, that's all that's left on the bottom. And at this point, we can just plug in 4. So you got 4 plus 4 on the top and 4 lots of 4 squared on the bottom. So it's negative 8 on the top, 64 on the bottom, negative 1/8. We have now found the slope of the tangent line to the fraction 4 over x squared at the x coordinate of 4. It is negative 1/8. Which means, isn't its tangent line pointing down the way then, right? So it's pointing this, it's pointing that way, right? Let's see if I can do something visual. Why don't you put your attendance down, your last name, while I'm doing this? Okay, that looks good. Right, so I've just loaded up Desmos and I put 4 over x squared. Okay, imagine 4 over x squared, isn't it just going to be a vertical asymptote to x equals 0? And doesn't it look like a volcano, right? So it shouldn't surprise you when you see it, because that's what it is. There it is there. Now, we were interested at 4, right? So if I move this and I zoom in here, there. Does it look reasonable that the slope of that tangent line is negative and negative 1/8 could be okay, right? There's no way of getting the numerical part of that. So just curious, you never know what Desmos can do. Will it do that? Nah, okay. I'm just curious. Well, have I sort of approved that it works, at least visually, it doesn't contradict things. Right. So stop that share. And I haven't actually looked at any homework questions yet.
Oh, could
So-
you go
Mhm.
back to that problem we just did on the paper
Sure.
for a moment?
We are there. Good.
Oh,
So-
okay.
Right. So I'm looking right now at the homework questions, and they are pretty much what I would have expected. Although it's been a while since I looked. They're going to ask you to do find the slope of the tangent line, which is pretty much what I was expecting. And then the added thing that I haven't done yet, which is find the equation of the tangent line. So I want you to imagine that we had some kind of quadratic, right? There it is. And we're interested in finding the slope of the tangent line, say at x equals 2. And that's all we've done today, right? We found the slope of that tangent line. But I'd like to know the equation of that, right? I'd like to know that it was like 3x plus 1 or whatever it is, right? So let's add that to our puzzle. So I'm going to pick a nice quadratic because they're easiest to do. And it's going to be x squared plus 4x plus 1. And I'm interested in the point 1, 6, right? So pretend that now is 1, right? So we're going to find the slope of the tangent line to this curve at that point. Now, what you have to do here is to realize that isn't that the x coordinate, your A. Right, so they don't tell you the way this one's being phrased, they don't tell you A is 1, right? But you can tell since the x coordinate of P is 1, that's who A is. I have 2 different formulas. We now can do things using this formula. And we can also do it using the one that we started today with, which I'm busily trying to find. It's obviously going to be the last piece of paper. Or we could use that formula. Right. So to make my life easy, I'm going to write them both here. That way I don't need to keep looking through pieces of paper. You can find the slope of the tangent line at any given point A by using that formula. You can also find the derivative of the tangent line by using the second formula. So when you have a choice, wouldn't it be nice if there was a rule about which one you should use in which situation? So let me tell you a kind of broad rule that works the vast majority of the times. If your function is a polynomial, right, f of x equals x cubed plus 2x, f of x is x squared plus 4x plus 1. Anytime you have a polynomial, use the top one. Will you trust me? The math is easier. Right? Just take my word for it. Why is it easier? Because if you try and use this formula, you're going to have a really hard time factoring. Because you'll use the factor and cancel method, and as long as it's only a quadratic, you're okay. But the minute it becomes x cubed or anything bigger, I'll give you an example. If I said to you factor x cubed minus 6x squared plus 9x plus 3, would you agree you're going to have a hard time? You don't want to do that. So use this method and you won't need to. So polynomials, there's my general rule. Use the top one. If you are doing fractions, 4 over x, 5 over x squared, right? Those kind of situations, you're not going to get horrible fractions, right? Typically, they're going to be pretty straightforward. But if you get fractions, rationals, I guess I should call them, use that one. That would be my advice. Now, if you get a question that involves square roots, you know, like 2 square root of x or something similar, right? If it's a 2 square root of x, use this guy. If it's a fraction with the square root of x, use this guy, right? So it depends on where the square root is, which one of those that you should use. Now, theoretically, you can use either method in either situation. It's just that the math will get uglier with one version than the other. And some questions, it doesn't matter which one you use. The math is just ugly both ways, right? So if you start a question using this method and then you say, oh God, I don't want to do this, you might want to restart it using that one. Remember the 4 over x squared one that I did? Right, I got to that point and I thought, oh God, I don't like the looks of this. This is not going to end well. Well, start again. Of course, if the second method is equally ugly, you've just found an ugly question, right? And so you're just going to have to fight your way through whatever method you've fixed on. So based on what I've just said, won't we use this method here then, right? This limit. So the derivative at 1. Instead of saying the slope of the tangent line to the function f of x at x equals 1, can I now say the derivative at 1? Or even better, can't I just say f dashed of 1 and you all know what we're doing? Agreed? F dashed of 1 is code for finding the slope of the tangent line to f of x at x equals 1. So it's going to be the limit as h tends to 0 of f of 1 plus h. Take away f of 1 over h. And so this is going to be the limit as h tends to 0 of 1 plus h squared, 4 lots of 1 plus h, add 1, take away f of 1, which is what, 1 squared plus 4 plus h, take away 6. All over h. You FOIL that guy out, you will get that. Distribute that, you get this. Now, I have an h squared. Check. I have 2 plus 4 more. I have 6h. I have a 1, a 4, a 1, and a takeaway 6. Oh, isn't that good news? Isn't 6 takeaway 6 0? So I can save a line of working. All over h. What I can now do is pull out h as a common factor. Then cancel. And I now have the limit as h tends to 0 of h plus 6, which is 0 plus 6, which means f dashed of 1 is 6. There, haven't we found the slope of the tangent line? It's a nice number. It's 6. And that's all we've done today. So let's do the second piece. Once you've found the slope of the tangent line, which in this case is 6, we now need to find the equation of that line. Okay. Well, what do I know? I know that this line passes through the point P, and I know that the slope of this line, because it's the same as the slope of the tangent line, is 6. And I want to find the equation of a line. Imagine that's the 0.16 and that's slope. I want to find the equation of a line that passes through a given point with a given slope. We have a formula for that. If I call this guy x1, y1, can anybody remember the formula for getting the equation of a line passing through a point with a given slope?
Yeah, I think it's oh gosh, isn't it a y2 minus y1 equals the slope of the line times the quantity x2 minus x1 plus b?
I'm not sure where that came from, but bits of what you said were right and other bits were. That's the formula. So we don't.
Y equals mx plus b.
Y equals mx plus b would be only useful if this was a y-intercept, in which case you could do it. But in general, this point is not an intercept, right? So you have to use what's called the point slope equation.
Okay.
So this is the only guy in town, right? This guy will do all situations. So x1, y1 are the coordinates of the point, and m will be the slope. Okay. Now it sounds like, Keith, you were mixing the formula for getting a slope, which is y2 minus y1 over x to take away x1. Sounds like you were using a bit of that guy along with some equation stuff. So this is the guy that you're going to use. It's called the point slope equation. So y take away 6, oh, by coincidence, 6, x take away 1. Y take away 6 is 6x take away 6. Add 6 to both sides. No. Cool. The equation is y equals 6x. I have got to sketch this. That is such a nice answer. Well, let's zoom over to Desmos and check that that's the case. So our function f of x was equal to x squared plus 4x add 1. And I'll move this around and shrink it back. Pretty nondescript, agreed, it's just a polynomial. And I was interested in at the 0.16. So where would 16 be? Let's put 0.16 in so that we can see it. Right, so I'm interested in the tangent line right there, okay? Now, if this works, we should have a tangent line with equation y equals 6x. Does that look like a tangent line to you? Right? So I'm really happy about that. Now let's just pretend I screwed up. Not that I've ever done that. Do you see how this purple line does not look like it's a tangent line anymore, right? It doesn't go anywhere near the point of interest. So I know that we are good. Now I probably could do some things here. I don't know if zooming out helps. Does zoom out help or hinder the process? Does that look pretty much bang on? Right. Now, if you zoom in on a tangent line, something really interesting happens, and it always happens. There. Do you see that the curve and the tangent line are almost indistinguishable from each other? And what that is telling us is that in small regions of space, isn't the tangent line virtually the same thing as the curve? And that actually gets used in a later topic called linear approximations, where you actually take the derivative and use it to estimate the value of a function. Pretty cool. I was not expecting such a nice answer. I just randomly picked questions, and you know when you normally pick, when I normally pick a question, don't you get the slope is 7/15 and the straight line is 43 9th x minus 7/52? I mean, that's what I normally get when I pick things at random. Because they're random, right? Anything could happen when it's random. So it was kind of nice that that came out as a really pretty answer. I'm happy. I haven't asked this for a while. I guess I'll just get too caught up on how cool this is. Has anybody got any questions so far? We've now got a really I don't know what word that is. A really interesting way of solving a problem that was a big deal. I mean, we don't think of things as big deals, but if you went back, I think it would be 400 years ago, before they had solved this problem, if you had came up with a solution, you would be like the Einstein of the day. You would be, wow, how did you even think of tackling it that way? Because in fact, to be able to tackle this question, didn't you have to first create the idea of what a limit was? And then we have to figure out how to find limits. So if you're wondering, why did we spend all that time looking at different ways to find limits, like conjugate method, factor and cancel method, all the other tricks of the trade? Well, you needed that skill set before this would even be useful, right? So it's a bit like you can't do A before B, right? You got to do one before the other. And a little history, just to and then we'll continue with this. Does anybody actually know who is credited with solving this problem? In other words, the creator of calculus. Historically, who gets the credit?
What was the question again?
Who gets the credit for creating calculus, for solving the tangent line problem? Anyone know? You've actually, when I tell you, then you'll say, "Oh, I've heard of him," or them.
Aristotle.
Oh God, it would be cool if he had done it. That would
That'd
have
been a long
gave,
time ago.
that would have been a long time ago, and people would.
Is it Newton?
Yeah.
It was Newton.
Hmm.
Sir Isaac Newton. You know the guy, gravity, ball fall, apple falling in his head. That guy, right? He is credited with discovering the solution to the tangent line problem. So I'll give you a little story behind that. There is a second person called Leibniz who is also given credit. And depends on your perspective, which one of those gets the most credit, or only one of them gets credit. So I'll tell you a little story. According to Sir Isaac Newton, that's where my view is, he figured this out, right? He did limits, he had to create limits, he had to figure it out, and he came up with it. And then he tested it, and it worked. In other words, he found, situations where you needed to know exact values, from physics, from the movement of planets and all those kind of things. And it works really elegantly. In fact, it allowed them to predict the motions of planets in a very precise way. Up to that point, we were using, like Aristotle, right? We were using classic Greek algebra. It was really painful to do it that way. And this calculus, and he used it, and it was great. And he kept it as a secret. And it's a kind of, if you find something really cool, but it allows you to get the answer and find things that nobody else can find. He published the things he found, but he proved them using the old Greek algebra, right? He used it the same way that everybody, because if you know the answer, isn't it kind of easier to prove it? So he knew what the answer was going to be using calculus, and then he just proved it, published books, planetary motion, and he was really happy with it, but he kept it a secret. And in those days, mathematicians, scientists communicated by Latin, right? It was like the international language. So a Frenchman and a German and an Englishman didn't need to know French, German, and English because they all knew Latin, right? It was a way of communicating. So he contacted Leibniz and said to Leibniz, "Hey, Leibniz, I got to show you this cool piece of math. I've solved the tangent line problem. Here are some equations I used. Here's some examples. Is this not cool? Oh, and by the way, I've used it to prove planetary motions and velocities and accelerations, and it's really cool stuff." And according to Newton, at least, Leibniz stole the idea and published basically a pamphlet saying, "Hey guys, look, I've solved the tangent line problem. Here is how I did it, and here are the solutions and how you can use it." And of course, Newton was not a happy soul, and he basically told all the British scientists, I sent him a letter telling them everything. He stole my stuff. You imagine that's bad news, right? Now, that's my perspective. The German Leibniz, his story was, I had also solved the tangent line problem. And I kept it as a secret. And I found out all sorts of cool stuff. And I was using, just like Newton did, his stuff. And I was using it to show people movement of objects and, velocity, acceleration and forces and all sorts of cool stuff. And, the branches of science that I was interested in. And then I got this letter from Newton. And he had the same idea as me. And I thought, well, I better publish first before he does, because I invented it first. And that was his explanation. And so it caused a big controversy, because up to that point, there was a kind of unwritten rule, right? That you could communicate with other scientists, but they weren't going to steal your ideas, right? You would use it as a way of communicating information, right? A good way of saying it. And it caused an awful lot of people not wanting to communicate with anyone. And so that's the story behind it. So if you are a European from, say, France or Germany, Leibniz solved the tangent line problem, and Newton was just being grumpy because he never published. And if he'd published, he would have got all the credit. Or if you're on the British side of things, Leibniz is a thief and stole someone else's idea. And from my perspective, Leibniz is a German, and it's not like a German did anything bad.
Oh man, that's cold.
Oh, Keith gets that one. Okay. We're ready for our next question. Okay, guys. So a little bit of history behind it. Mathematicians weren't always geeks. People get shot and had duels over mathematics back in the day, right? People would get killed for it. But
Serious? They actually duel over math?
Oh, yes.
Wow.
Galois had a running hatred with Gauss, and they had duels. I mean, there were rules to it. Normally, the rule would be if the first person to quit or the first person to draw blood, you would stop. Right? So you didn't necessarily die most of the time. But yes, it's the equivalent of being in a bar and somebody challenging you to a fight because you insulted their mother, right?
Yeah,
you normally don't get killed, but there's a fight.
I can just see a couple of nerds duking it out. They're like this.
Well, they used guns and swords, so it was a little bit different than doing that. Okay, let me pick one at random from that list then. That's a quadratic. We've done tons of quadratics. Let's see if I can pick something else for our next question. Okay, this one's pretty messy. And this one is a version of question 5. And it's a square root function. And we're being asked to find the slope of the tangent line at the point -1, 3. In fact, we're not even asked to find that. They ask us to find the equation of the tangent line. So in this case, you're going to look at this as a two-step process. Aren't we still going to find the slope of the tangent line using one of these two? And then we're going to do the y minus y1 bit to answer their question. Which one of these two do you think I should be using in this particular question? Any preference?
I'm going to go for the top one.
Okay. The bottom one actually would work okay. These are not hard and fast rules. You can use any of these methods in any situation. Just sometimes the math is easier, right? That's the only prerequisite. So we'll do that one. So A here is going to be -1. So I'm going to find f dashed of -1. And it's going to be the limit as h tends to 0 of f of 1 plus h, take away f of 1, all over h. So it's going to be the limit as h tends to 0. Right, f of 1 plus h basically goes inside here. So it's going to be 4 take away 5 lots of 1 plus h. And what is f of 1? F of 1 is 3. Or f of -1. Oh, shooting space. Just caught myself. Isn't a -1, right? So it's -1 plus h. There we go. Just caught myself. It's -1, right? So it's -1 plus h. 4 take away 5 lots of -1 plus h. So this now becomes the limit as h tends to 0. This is kind of messy. I think I'll probably do this in one go. Here goes. -5 times -1 is 5. So 4 plus 5 gets me 9. -5 times h is -5h. Are you okay with 9 minus 5h, or do you want to see a middle line? Right. 4 take away 5 lots of 9 -1 plus h eventually gets you 9 take away 5h. We go with that? Okay. Do you recognize that this definitely needs what's called the conjugate method, which you kind of could have seen coming? So it's going to be the square root of 9 take away 5h, add 3, square root of 9 take away 5h, add 3. So it's now going to be the limit as h tends to 0. And the two guys in the bottom are just going to be left alone. Now, if you multiply this guy by its conjugate, right? I could do another one of those long foils, but let's show you the shortcut. Isn't the shortcut the first guy squared, take away the second guy squared? So the first guy squared gets you 9 take away 5h minus the second guy squared. Are you comfortable with that shortcut? So I don't have to foil it all the time, right? When you do a thing and its conjugate, you always end up with the first guy squared, take away the second guy squared. And this in turn, oops. Well, they cancel out and you're left with negative 5h on the top and this guy on the bottom. One for one cancel, which is exactly what I would have expected. So it's negative 5 over this guy plus 3. And now I can just put 0 here. So what does that get me? 9 take away 5 zeros is still 0. 9 take away 0 is 9. Square root of 9 is 3. I get 3 plus 3. And the answer is negative 5, 6. So I know the slope of the tangent line is negative 5, 6. We comfortable with that? Exact value, negative 5, 6. I know the point of interest. I know the slope of the tangent line. So I should be able to get the equation of the tangent line by doing the point slope equation. This guy is called x1, y1. So it's going to be y take away 3 is equal to negative 5, 6 x take away negative 1. I guess now that I've written it that way, I'm going to have to do one more line. Should have thought that through, right? Got that. Distribute the negative 5, 6. Add 3 to both sides. Now you're going to have to sometimes deal with some awkward values here. Fractions in particular I'm talking about. So I'm going to take negative 5, 6 and just add 3 to it and then make the answer a fraction. So there's, show you, negative button down here, negative 5, 6, and add 3 to it. And then math button, choice 1, and that turns into positive 13/6. And there is the equation of our tangent line. And I'm now going to go into Desmos. And we are going to check that that works. So it's a square root of 4 minus 5x. So square root of 4 take away 5x. The point of interest was negative 1, 3. So I might as well use that guy. Don't worry about the fact you can't see it over there. We'll adjust the window to suit that. Now it's going to be negative 5, 6 x plus 13/6. Okay, now Oh God, I am so happy. Can you see the tangent line exactly where it should be? Let me just zoom in a little bit more. There. I think that's pretty conclusive proof that this method is doing what it says it does, isn't it? It's giving you tangent lines. And I suspect, I'm just making this up, but I suspect the reason why most of the homework questions get you to find the equation of the tangent line rather than just find the slope of it, right, is so that you could put it in Desmos and check it, right? So you could have a quick look. I will be doing questions like this in the midterm, at least one. So I'm almost certainly going to do the same thing and ask you for the tangent equation in the tangent line, because as I say, that's a good way to see it. Let's pretend for a minute, not that I've ever done this, that I made a mistake. Can you see that they never match, right? That's pretty clear. Let's suppose that I made a different mistake and I got my signs wrong. I mean, when you get it wrong, isn't it pretty obvious you got it wrong? If you have the equation of the tangent line as part of your question. Right, again, any questions? We're good? Right, for the last few moments then,